When air flows over a wing, it does not all move the same way. Right at the surface of the wing, the air is slowed down by friction. You can imagine the wing grabbing the air a little bit. The air touching the surface almost stops. A tiny bit above it, the air can move but only slowly. Higher up, it moves faster, and even higher it finally reaches the normal airflow speed. So if you look from the wing outward, the airspeed is like a ramp. Zero at the surface, slow just above it, faster and faster the farther you go away. This whole thin zone where the speed changes from stop to fast is called the boundary layer. It's not thick, only a few inches, but it is extremely important because everything that happens on the wing depends on how this thin layer behaves. At the very front of the wing, the boundary layer usually starts in a very calm way. The air moves in smooth, clean layers. These layers slide over each other without much mixing. This is called a laminar boundary layer. You can imagine it like a calm river, where all the water flows nicely in the same direction without waves. Laminar flow is very smooth and creates little friction, which means low drag. That is good for speed and saving fuel. But this smooth flow does not stay smooth forever. As the air moves farther back along the wing, it gets disturbed by tiny bumps, dirt, insects, rain, vibration, and changes in pressure. Little by little, the smooth layer starts to shake and lose their order. At some point, they break up. This moment is called the transition. On many normal wings, this transition often happens near the thickest part of the wing. Before that point, the pressure usually gets lower, which helps the flow stay calm. After the thickest point, the pressure starts to rise again. Now, the air has to fill uphill against pressure. And that makes the laminar flow unstable. That is why the change to turbulent flow often starts around here. But not all wings are the same. Some wings are designed as laminar flow wings or laminar profiles. On these wings, the thickest point is moved farther back. This keeps the pressure low for a longer distance, so the airflow can stay laminar much longer than on a normal wing. If the surface is very smooth and clean, the transition can happen far back on the wing. After the transition, the boundary layer becomes turbulent. Turbulent boundary layer is messy and chaotic. The air is full of tiny swirls and little whirlwinds. This creates more friction, so turbulent flow has more drag than laminar flow. Even though turbulent flow has more drag, it is also stronger, because the air is mixing. It has more energy near the wing surface. It helps the air stay attached to the wing longer, especially when the wing is at a high angle or the air has to flow uphill. So laminar flow is good for low drag and turbulent flow is good for staying attached. In the end, the boundary layer is small, but it decides a lot. If it stays smooth and laminar, the airplane flies with less drag and uses less fuel. If it becomes turbulent, it has more drag, but it is also stronger and can follow the wing better. Designers always try to find the best balance between these two. Sometimes the airflow wants to separate too early, especially at low speed, high angle of attack or near flaps and control surfaces. That is when some airplanes use Vortex generators. These are small fins or bumps on the wing or near the tail. Vortex generators creates tiny spinning air movements. These little swirls pull fast air from outside the boundary layer down into slow air close to the wing. This gives the boundary layer more energy. With more energy, the air can stay attached to the wing longer and does not break away so easily. So, even though vortex generators makes the flow more turbulent earlier, this is done on purpose. The goal is not low drag, but safe and stable airflow.